Okay, so we're back from our little break here, and I want to discuss three more notions that are very important in complex numbers. I just want to emphasize something which may be obvious, but nevertheless I want to say it. It's very important to practice a lot when you see new things, okay? If you haven't seen complex numbers before, and it turns out that some of you haven't, it's extremely important to get your hands dirty, to do a lot of even seemingly completely silly exercises, like take two complex numbers and add them. See that you can do the addition correctly. Subtract complex numbers. Multiply complex numbers. Draw complex numbers geometrically. Draw them on the two-dimensional plane as a plus bi, right? You have to do these things until you feel that they're entirely yours, that you can do them, and just like you can do addition in real numbers, okay? Otherwise, if you just see and feel that you understand, once you get to the point where you have to do something on your own, you'll find yourself very not secure, not you won't feel good about it, okay? You won't feel that you can, you have to get to the point where everything is yours, it's in your hands. You don't think when you multiply two complex numbers, because just like you don't think when you multiply two real numbers. Sometimes you don't know how to multiply, right? If I ask you what is 275,486 times 73, you'd have to take a calculator. But you know essentially what the operation means, how you do it. Okay? Okay, so I'm sorry for sometimes sounding like your mommy, but I'm a parent here. Okay, what is the complex conjugate? So here's the definition. Suppose you have the number, so for z equals a plus bi, we define the conjugate, the complex conjugate, to be z bar. We denote it with a bar over it, and it's simply defined to be the same real part and the same imaginary part, but with a minus sign. So the conjugate of a plus bi is a minus bi. Geometrically, since we have a geometric interpretation of complex numbers, so suppose this is the number z equals 3 plus I, right? You can see that this is 1 on the imaginary axis, and this is 3 on the real axis, so this is 3 plus I. What is its conjugate? Right, it's going to be 3 minus I, so it's going to live down here. Z bar is 3 minus I. And you can see that a number and its conjugate are always mirror images with respect to the real axis, right? Suppose, let's take a different one. Suppose we have w, let's say over here. So this is the number w, which is minus 4, let's say, minus 2i. There's w, minus 4 minus 2i. What is its conjugate? It's going to be minus 4 minus 2i, right? We have to change the sign of the imaginary part, so it's going to be minus 4 plus 2i, somewhere here. W bar is minus 4 plus 2i. Good? So a number and its conjugate are always mirror images with respect to the real axis. This is minus 4 here, and this is minus 2 and plus 2. If I want to add too many details, I'm going to have to extend the imaginary axis, but you can see the idea. Okay, good? Is it clear? Okay, let's write some properties of the complex conjugate. Properties. when I write something like properties, actually it's a theorem. And it's going to have several parts, and you need to prove them. And we know how to prove these sort of things. You have to take a general form of a complex number and show the properties, just like you did when you practiced and showed that the properties of being a field hold for the complex numbers. So this is a theorem. It requires proof. It's very easy, so I'm just going to spell out all the parts, and I'm going to do one as an example. So if you take z plus w and take the conjugate, it's the same as the conjugate of z plus the conjugate of w. Okay, so the conjugate of a sum is the sum of the conjugates. In fact, it's also true for subtraction, and instead of writing it again, people often write z plus or minus, and likewise here. Okay, is it clear what the theorem says? Okay, is it clear how to go along proving something like this? You take a z, a plus bi, you take a w, c plus di, see what you get on this side, see what you get on this side, and see that you get the same thing. Okay, good? Okay, part 2, if you take a product and then take the conjugate, it's the same as the product of the conjugates. Okay. Part 3, if you take a number and add it to its conjugate, what do you get? So let's think out loud. We're actually thinking the proof here. A plus bi plus a minus bi. So the plus bi and the minus bi cancel out. So we just get 2a. So the way to write it is we get 2 times the real part of z. Z and z bar have the same real part, right? They only have a different imaginary part and different only by a sign. And that's this formula. You can call it a formula, but it's really a very obvious observation, and we just proved it. Good? Everybody? Okay. So what if we subtract? What is z minus z bar? Right, the real parts will cancel out now, right? So this is a plus bi minus a minus bi minus a minus bi. So a minus a dies. We're only left with an imaginary part. And how much of it are we left with? There's a bi here, and there's a minus bi here, right? So there's 2 bi's. So it's 2 times the imaginary part of z times I. Okay, good? Everybody? Okay. Part 5, z equals to its conjugate. Z equals to its conjugate implies, when is a number the same as its conjugate? When is a plus bi the same as a minus bi? Right, it has to be a real number. Okay, it has to live. If you look back here a second, remember that the conjugate is a mirror image, right? So the number can be the same as its conjugate, only if to start with it lives on the real axis, if it's a real number. Okay? So this implies that z belongs, or maybe let's write it more formally, that the imaginary part of z is 0. Okay, so that z is actually real. It's of the form a plus 0b. Okay, and in fact, this is an if and only if statement. So this implies this, but vice versa. If a number has a 0 imaginary part, then it's going to be equal to its conjugate. And the way we denote it is with this double arrow going both ways. So this is a statement that this implies this, and simultaneously this implies this. It's a two-way statement. Finally, part 6, z times its conjugate is always greater than or equal to 0, and z times its conjugate is equal to 0 if and only if, I want a bit more space here, z times its conjugate is equal to 0 if and only if, that's how we read this two-way implication, if and only if z is 0, is the complex 0. Okay? So I said I'm going to prove just one of them, but in fact, while stating them, I kind of said the proof of almost all of them. But this one I want to prove in detail. I want to actually spell out the proof. So here's the proof of 6 in detail. Proof of 6. So what is z times z bar? Z times z bar is z is a plus bi. Z bar is a minus bi. That's the most general form of a complex number, a plus bi. Multiplied by its conjugate, let's see what we get. We get a times a squared, plus bi times minus bi. So it's minus b squared, I squared. But I squared is -1, so it's plus b squared. Does everybody agree to this, that this is the real part? bi times minus bi is minus b squared times -1, plus b squared. And then there's no imaginary part, because a times minus bi cancels out with bi times a. Okay? So this is it. This is what we get. And this is a non-negative real number. It's the sum of two squares of real numbers. So this is a non-negative real number. Does everybody agree? So that's the proof of this first half of statement number 6. Okay? And I want to make a very important remark here. Whenever you see this sign, this order sign, saying that one side is bigger than or greater than or equal to or less than or equal to, this automatically means that you're dealing with real numbers. There's no order on the complex numbers. The complex numbers live in a plane, in a two-dimensional space, and it's meaningless to say that 3 plus 5i is bigger than -2 plus 17i. Okay? You can compare separately the real part, and you compare separately the imaginary part, but when you get 2 points on the complex plane, let's look here for a second, which is bigger? Is this number bigger than this number? Is this number bigger than this number? Look, this one has a bigger imaginary part, but a negative real part. How does it compare to this one? Okay? And if you take numbers that, if you think of maybe who is further away from the origin, then these two numbers are precisely the same distance from the origin. Okay? So there are ways to try, there are good ways to try and think of an order on the complex numbers, but they don't do the job when they're needed later on. So in fact, there's no good ordering on the complex numbers. So whenever you see this symbol, this automatically indicates that in particular, this is probably a real number. And in fact, it is. When you take a number and multiply it by its conjugate, what you get is real. Okay, A is real, B is real, their sum of square is real, and in particular it's non-negative, so we can say this statement. Is that clear? Okay, good? Yes, question. You're absolutely correct. I said that you can attempt to define orderings on the complex numbers. For example, like you do a lexicographic order, like you do in a dictionary. Okay, look first at the reals and then but you get weird things. Okay, you would get that the number 2 plus 1,000,000 I is bigger than 1 minus 500 I. Okay, 2 plus 1,000,000 I is that 1 plus 1,000,000 I is less than 2 plus 5i. Okay, if you try to do this, look first at the reals and then at the... So you get weird things that are not compatible with reasonable things you want to require later. So I'm not saying it's impossible to define some sort of ordering on the complex numbers. There's just not a useful one that people define. That's the statement. Okay, good? Okay, we're not done with the proof of 6, because 6 had a second part, that this product is 0 if and only if z is 0 itself. So this product equals this, and this could be 0. This is always greater than or equal to 0, but it can only be 0 if both a and b are themselves 0, which means that z was 0 plus 0i, therefore z is 0. So in particular, zz bar equals 0 if and only if a equals b equals 0, meaning that z is itself 0. Okay, clear? So this is really spelling out the proof of property number 6, which is very useful. We're going to use it even in a few seconds. Okay, so when you take a number, multiply it by its conjugate, you get a squared plus b squared, and in particular, it's a non-negative real number. Okay. So this kind of summarizes our initial discussion of the complex conjugate, and now I want to discuss another term that relates to complex numbers, the modulus. So what is the modulus? So here's the definition. For z equals a plus bi, we define the modulus to be, we denote it by two vertical bars that really remind us of the absolute value in real numbers. And in fact, it's sometimes even called the absolute value. Okay? It's the same thing. And we define it to be, this is going to look weird, the root of z bar. That's how we define it. But if you think for a minute, what is z bar? We just proved that z bar is a squared plus b squared. So this is in fact a real number, a non-negative real number. It makes sense to put it in a root like this. And what we get is the root of a squared plus b squared, which are the real and imaginary components of z. And what is this thing? Why do we define it? And why do we call it the modulus and denote it by this absolute value sign? The reason is, so geometrically, a geometric interpretation is, if you think of a complex number in the complex plane, here it is. Here is z equals a plus bi. That means that this is a and this is b, right? That's how we think of complex numbers. The real part is a, the imaginary part is b, and so if we draw a triangle here, if we draw a triangle like this, it's going to be a right triangle where this side is precisely b, right? It's precisely of length b. This side is precisely of length a, and this side here is precisely the length of the vector z, the length of the vector corresponding to z. Remember we mentioned vectors briefly? Or you can think of just the length of the hypotenuse. And by Pythagoras, a squared plus b squared is this modulus of z squared, right? Pythagoras, or Pythagoras, depending on which part of Greece you're from. Pythagoras, anyway, it should be a capital P, right? It's his name. Pythagoras tells us that a squared plus b squared is precisely the length of the hypotenuse squared. And therefore the length of the hypotenuse is the root of a squared plus b squared. Okay? So what this thing measures is the distance of the point z from the origin. Z is the distance of z, the absolute value of z, or the modulus of z, is precisely the distance of the complex number z from 0, from the origin. Okay? And in that sense, it corresponds to the absolute value in real numbers. The absolute value of a number, let's say 5 or -5, is always the distance to 0 on the real axis. Okay, so it extends this same thing for real numbers. Okay, clear? Everybody good? So is it clear what this measures? Okay. Let's, okay, yeah, I'll write it. So z is the distance of z from 0. And let's write, and the length of the vector corresponding to z. Okay, so if you think of this as the vector z, and many of you told me that you have done these sort of things, especially in physics in high school. So if you think of this as the vector z, this is precisely the same notation that is used when discussing vectors. This is precisely the notation used to indicate the length of a vector for the exact same reason. So everything fits in nicely because it's just two ways of thinking of the same thing. It's not anything new. Okay? So if this confuses you, don't worry about it. This is sufficient, but this is precisely when you will encounter vectors in more detail, you will see that the length of a vector is precisely the modulus of the complex number sitting at the tip of the vector, starting when the vector is planted at the origin. Okay? Okay. Let's write some properties of the modulus. Again, this is a theorem, and again, it needs proof. So here's the list. So the first one is that z times z bar is the same as the modulus of z squared. Okay, remember, by the definition, it's in the definition, the modulus of z is the root of z times z bar. So this squared equals this squared. Okay, and both sides are real numbers. Okay, the modulus is a real number. Okay, let's look back here a minute. The modulus is a real number, right? Look here for a second, please. Hello, thank you. The modulus is a real number. Okay, so this is important. And this is a real number. We know that as well. That was it's not just real, it's positive, and that was the last property for the complex conjugate. Okay, so that's the first property we have here. Part 2, the modulus of z bar is the same as the modulus of z. Okay, this has a different imaginary part. Its imaginary part is not b, it's minus b, but when you square them and take a root, you get the same thing. Okay, that's the proof of number 2. Very easy. Number 3, the modulus is always greater than or equal to 0. Okay, it's the root of a sum of squares, of real numbers. Okay, that's the proof of that. And the modulus is equal to 0 if and only if you're looking at z equals 0. This is the only number for which its modulus, its distance from the origin, is precisely 0. Okay? Number 4. The real part of z, this is a real number. This is a, right? Z is a plus bi. This is a. I can take its absolute value. This is again a real number, a positive real number. It's the absolute value of the real part of a complex number. Okay, confusing, but think. Z is a plus ib. Its real part is just that a. It's a real number. So this denotes the absolute value of the real part is less than or equal to the modulus of z. And likewise, the absolute value of the real number imaginary part of z is less than or equal to the modulus of z. Why are these true? Why are these true? The easiest way to see them and to connect to them, to look at them and say, of course it's true, is to look at that picture again. Let's look at this picture again on this board. This is the real part of z. Do you agree? And this is the imaginary part of z. And this is the modulus. So obviously this is less than or equal to the hypotenuse. The hypotenuse is always greater than both edges in a right triangle, right? That's how to see that property. If you want to do it algebraically and plug in the a's and the b's and so on, it's also pretty obvious, because on that side you get a is less than the root of a squared plus b squared, and likewise you get it over there. So it's easy to prove algebraically, but it's also good to see why it's true geometrically. Okay. Property number 5, if you take two numbers and add them and take the modulus, it's less than or equal to the sum of the moduli. This has a name. This is called, right, the triangle inequality. That's what it's called. Proving it algebraically is somewhat more tricky. Okay, you can do it. It's not too hard, but it's not a half-liner. You have to write a bit. Okay, but the geometric proof of this is very easy. Okay, if you remember that addition of complex numbers corresponds to addition of vectors. So the idea of this, the geometric idea, I'll draw a little picture here, So suppose that, let's say, this is z, this corresponds to z, and therefore the length here is the modulus of z, and let's think of this as a vector, okay, of length modulus z. Okay, let's just call, okay, this is confusing what I'm doing. So this is the vector corresponding to z, and let's have another vector corresponding to w here. So this corresponds to w, and remember how we add them. How we add vectors. We draw w starting where z ends, and then we take the diagonal of this parallelogram that we get. So this in red is z plus w, right? And this statement merely says that the length of the diagonal, the length of the vector z plus w, the red one, is greater, is less than the length of z plus the length of w, okay, which corresponds to the statement that taking the straight line between 2 points is always the shortest distance, and in particular shorter than going via a third point. Okay, so z length plus w length is greater than or equal to going the straight way, z plus w. Okay, and that's why it's called the triangle inequality. Okay, this, by the way, is a valid statement for absolute values of real numbers. In fact, it's called the triangle inequality there as well, as you probably know, but its geometric meaning in real numbers, when everything is one-dimensional, is kind of blurry. Okay, in 2 dimensions, you really see why it's called the triangle inequality. Good? Everybody? Okay. And one last property is that if you take the product and take the modulus, that equals the product of the moduli. Again, very straightforward proof, but you can try spelling it out. Okay? A very common mistake is to write an equality here, sometimes very tempting, but it's not true. It's in fact an inequality. Okay. Okay, so once we have the modulus and we have the conjugate, we can finally define something that we've been kind of only mentioning so far, division. How do we divide two complex numbers? And if you think for a minute, we haven't said anything about that yet. Okay, so let's define division of complex numbers. And before I write the actual definition, I want to show you where it comes from. Why what I'm going to write is indeed the definition. And if I just wrote the definition, it would be completely surprising. But if you see where it comes from, you'll see that in fact it's very natural. So let's start with an example. Suppose I want to divide 2 plus 3i divided by 4 minus I. I want to make this division. Okay? The way to do it, the standard way to do it, is to multiply the top and the bottom by the conjugate of the bottom, by the conjugate of the denominator. And this trick of multiplying by the conjugate, I would make a wild guess that you've encountered it before you ever knew anything about complex numbers, because it's done in the taking the sense of the word conjugate to real numbers. When you have 4 minus 5x, you would multiply by 4 plus 5x in order to simplify expressions. You may have done it when working on trig expressions or algebraic expressions. It's always the same idea. So I'm going to multiply, in order to carry out this division, I'm going to multiply by this number. This is just a way of writing 1, right? Something divided by itself is obviously 1. And what I get, which is the reason for doing this, so 4 minus I times 4 plus I, that's a number times its conjugate, it's 4 squared, 16, minus 4i plus 4i cancel out, and I get minus I squared. I squared is -1, so I get plus 1. That's what I get on the bottom. Do you agree? And on the top, I have a product. I have to calculate it. So it's 2 plus 4, it's 8, plus 3i times I. So 3i times I is 3i squared. I squared is -1, so we get 8 minus 3, plus, here I have 2i plus 12i. So 2 plus 12i, or in other words, 8 minus 3 is 5 plus 14i divided by 17. That's what I get. Do you agree? Okay? And this is already written as a complex number. In other words, this is the number 5 divided by 17, that's the real part, plus 14 divided by 17, I. So this is a complex number, and this complex number is the quotient of these two complex numbers. Okay? So how do we verify that, by the way? How do we verify that? We multiply. We take this, multiply by this, we should get this. So let's do that. Note, right? The division is the opposite operation, the inverse operation of multiplication. So if this divided by this is that, then that times this should be this. Let's check that. 5 over 17 plus 14 over 17i times 4 minus I this better be equal to 2 plus 3i. Let's verify that. So what do we get? We get 20 over 17, this times this, plus 14 over 17, I times negative I. I times negative I is negative I squared is 1. So we get plus 14 over 17. That's the real part. Plus, from here we get minus 5 over 17. Minus 5 over 17. And from here, oh boy, 4 times 14, that's 40 plus 16, 56 over 17. I. And this equals 20 plus 14 is 34, divided by 17 is 2. And here we have 56 minus 5 is 51, divided by 17 is 3. I. Okay? So indeed what we did here, without knowing the formula, without knowing anything, just by using a standard, reasonable sort of trick, we defined division. How do we divide two complex numbers? We multiply by the conjugate of the denominator. Okay? So the definition of division, which I'm going to write down now, which is going to look somewhat, let's say, unnatural, if you would see it without this preceding example, but it's actually very, very reasonable. Definition, z, a complex number, divided by w is z times w bar divided by w times w bar. Multiply the top and bottom by the conjugate of the bottom. So it's zw bar divided by ww bar. But what is ww bar? That's written here. Follow me here. What is something times its conjugate? It's the modulus squared. So dividing by ww bar is like dividing by modulus of w squared. That's the definition of how we divide two complex numbers. Z divided by w is zw bar divided by ww bar, which is the same as modulus of w squared. That's the definition. Okay? Good. So we did an example. I think this deserves a fancy blue box. Okay? And once again, you may think, wow, do we have to memorize this? No, you don't, because you know how to divide. You multiply the top and bottom by the conjugate, just like you do in many, many instances in algebra when you want to simplify expressions. This is just the way of saying it formally. Okay? Let's say some remarks and properties. Remark. Remember that we mentioned that C is a field. In particular, in being a field, it needs to have multiplicative inverses. Okay? So what is a multiplicative inverse? What is 1 over w? Okay? 1 over w, the multiplicative inverse is just, if you look at this, it's just w bar over modulus of w squared. That's the inverse. Okay? And that's the reason I postponed this, right? You need, if you want to write it in this very compact way, what you need is to know the conjugate and the modulus. These are the two notions that kind of appear in defining division and defining the inverse. Okay? So 1 over w, which is this number, is called the inverse of w. The multiplicative inverse of w. and denoted by w to the minus 1. Just like we denote multiplicative inverses in general in a field. Okay? And yeah, you need to practice. There's no shortcuts, okay? So practice. What do I mean by practice? Take any number, 3 plus I. Find 1 over 3 plus I. What is the inverse of 3 plus I? Okay, find it. It's not very hard. You can either memorize this formula, not recommended, or multiply top and bottom by 3 minus I. See what you get. Verify like we did. Whatever you get, multiply back by 3 plus I. See that you get 1. See that it's indeed the multiplicative inverse. Okay? And do a few more. Okay? Very important. Okay, some properties of division. This is kind of a lot to absorb in 2 hours of a lecture. Really, it's think of how much time you spent on real numbers, how you gradually throughout maybe elementary school and into middle school you learned about how to add and how to multiply and how to do inverses, which are fractions, and how to add them, and how you spent a lot of time on real numbers, just doing calculations with real numbers. And now we're, boom, in 2 hours, you need to absorb all this new world of numbers, which is not precisely the same as the real numbers. There are different things. There's no shortcut. You need to practice. Okay. Properties of division. I'm only going to list 2. If you take the quotient of 2 numbers, complex numbers, and take its conjugate, the conjugate of a quotient is the same as the quotient of the conjugates. This requires proof. And the second property is that if you take the modulus of a quotient, it's the same as the quotient of the moduli. Okay, so these are 2 theorems that require proof. I want to prove one of them. Let's do the second one. Okay, so proof of 2. How do we prove something? If you recall, when we had, for example, the axioms of a field, and then we had, after we finished writing the 11 axioms, we had some more little properties that hold in a field. For example, A times 0 is 0. A times the additive identity is the additive identity. Okay, that wasn't one of the axioms. It required proof, and we proved it. Okay, so when you prove little properties, you have 2 approaches. One, you can only use the axioms. You can do that here. You can write Z as A plus IB, write W as C plus ID, and then follow the definitions. Divide them just like you would divide Z times W bar divided by modulus of W squared. Whatever you get, take the modulus and see that you get the same thing on both sides. A bit tedious, but would work. Okay? Another thing you can do is prove it using properties that we already know. We had various properties of the modulus. We had various properties of the conjugate. We can use those properties to prove new properties. Once you proved something, it's as good as an axiom. If it's proved, it's valid. Okay? So I want to show you how to prove this, not by resorting back to the elementary way of writing complex numbers, but I want to use it to prove it using previous properties. So what is Z divided by W modulus? So by the definition of division, it's ZW conjugate divided by W absolute value or modulus squared. That's Z over W. And then this entire thing I have to take the modulus of. Do you agree? So this is just using the definition of division which we had on the previous board over here. Right? Look here a second, please. Hello? Thank you. So I'm using the definition of division in this step here. Is it clear? Okay. Now, here I have a product of three things. I want to rewrite it, just rewrite the same thing. So here's the outer modulus of this number, and I want to write it as a product of 1 over W squared. This is a real number. This is a real number. I can pull it out, times Z times W bar. Do you agree? Okay, I just rewrote this somewhat differently, but it's the same thing. Okay. Now, the modulus of a product is equal to the product of the moduli. That is one of the properties of the modulus that we had previously. Is it still on the board? Yes, over here. Look at this board. The product, the modulus of a product is the same as the product of the moduli. Okay, so that's what I'm going to use here. So this equals the modulus of 1 over modulus of W squared times the modulus of Z times the modulus of W bar. Do you agree? Okay, that's using property 6 that we had for the modulus. And now, this W modulus is already a real number. When I'm squaring it, when I'm squaring a real number, it's a real number, right? But when I'm squaring it, it's a non-negative real number. So this is a non-negative real number. It's reciprocal. 1 over it is still a non-negative real number. So for real numbers, the modulus is the same as the absolute value, and the absolute value of something non-negative, is just itself, right? The absolute value of 7 is 7. The absolute value of pi is pi. Okay? So I can remove this modulus notation or absolute value notation here is redundant. I don't need it. I can just write 1 over W modulus or absolute value squared, right? Here I'm going to leave Z modulus and not touch it. What about the modulus of the conjugate? Right, it's the same as the modulus of the original number. That was again a property that we had where over here. This is property 2. The modulus of Z bar and the modulus of Z are the same. So I can replace this with this, okay? And now this cancels out with one of these, and I just get Z over W. And if you look at the two sides, it's this, okay? I forgot to mention something very important, and some of you noticed it. I noticed that you noticed, but I didn't want to stop and something very important. We're dividing by W here. W better not be 0, okay? So these two properties are valid only when the number sitting in the denominator is non-zero. We can mention it here. W is not 0. But in fact, we should have mentioned it one board back when we defined division. So this is only valid when W is non-zero, and likewise here, okay? W cannot be 0 if we're going to divide by it. Good, everybody? And those that noticed and felt uncomfortable when I was doing all this stuff, very good. Okay, I just neglected it. Very bad me. But it's important. You can never divide by 0. Okay. So this wraps up the discussion of these three notions related to complex numbers, the complex conjugate, the modulus, and division, which are kind of related one to the other, as we see in the definition of division. What I want to do next is a different way of thinking of complex numbers, which is called polar form or trigonometric form. Okay? And the reason we want to resort to a different way of thinking of complex numbers is that in this different form, in this different way of thinking of them, doing multiplication and division, and in fact raising to higher powers and taking roots, becomes very, very easy. Whereas doing it in this algebraic form of a plus bi, it's pretty complicated. If you want to take a complex number and raise it to the power of 15, it becomes extremely messy. And in polar form, it's very easy. Okay? And that is thanks to a mathematician that we mentioned, de Moivre, that worked with this polar form and found these formulas for multiplication and division, which are very, very useful. So that we're going to do next.